Okay. Last class, I threw a lot of new, or maybe slightly new, or maybe quite confusing notation at you, which is the notation that'll help us convey some really basic ideas that I think we all kind of take for granted, which is physical laws should be invariant. They should not depend on who's looking, where they're looking from, how they choose to orient themselves or orient the system that they're observing. We know that. We know that certain quantities, vector quantities, tensor quantities, the stress in a material, the velocity at which something is moving at, shouldn't depend on who's measuring it and from where. And so I don't think these concepts are the challenging part. And I recognize that the new notation is something that I'm asking you to grapple quite a lot with without much time to sink your teeth into it. But it's really just a way for us to figure out, how do we switch between viewpoints? How do we take the way you're measuring something and switch to the way I'm measuring something? How do we measure things in a space? And why is that important? Why do we want to be able to do that? And then how do we adapt our calculus, which is, as we know, is the foundation to all of these physical systems that we've been looking at. We've been dealing all semester long with ordinary differential equations and kind of skirting around, but being aware of all the partial differential equations that govern these physical processes. So how do we handle kind of evaluating those things in different coordinate systems, and especially when we are forced to move towards more curvilinear coordinate systems, things that are not simple Euclidean X, Y, and Z orthonormal frames. I threw a lot at you. Today I'm going to throw a lot more at you. And like I said, this is to try to get you at least comfortable with the language and the ideas that we're going to be discussing, if not kind of the ability to go off and calculate some things. Although I will try to give you some things that you could try if you're interested. The other thing I will say, if this is something that is interesting or relevant to you and your work, and you would like to have some further reading on this topic, there are lots of books on tensor analysis. Many of them are written by engineers, kind of for engineers. In my experience, I found all of them to be, let's just say, written for someone who already sort of understands tensor analysis. And so that is really a painful introduction. So there's one book I found that really, it feels like it's actually written for humans who are coming to this for the first time. And that is a book entitled Einstein's Gravity in a Nutshell. And I think if you check out that book, you'll be pleasantly surprised to see a lot of the mathematics that we've covered in this class introduced and using this kind of this notation throughout. You'll see the first few chapters of the book have nothing to do with general relativity. They have to do with tensors, tensor analysis, calculus of variations, differential geometry. They talk about how to kind of perturb around a point. The math that is kind of the framework of the first several sections of that book is relevant to all the things we've discussed up until this point. And then beyond there, they start talking about things that might be less relevant to you. But I think that book is actually readable. Like sit down and kind of read and flip pages. And so I would highly recommend checking it out. Einstein's Gravity in a Nutshell. Okay, again, I'm going to kind of try to crash course through some of the basic topics that I want to convey in differential geometry. And I encourage you strongly to jump in and ask questions, and I'll do my best to answer them. Okay, so last class we hopefully became comfortable, or at least a little bit comfortable, with the metric tensor. And the metric tensor is our way of measuring distance in some coordinate system. And we would say, okay, there's some line element that has some length, and we're going to square that length. And we know that we can measure that line by writing down the metric tensor and contracting it with the differentials in that coordinate system. So this might be dx, dy, dz. In this case, let me give you a couple of like pieces of ways you'll typically see things. So for instance, you will usually see G with some subscripts or superscripts written as the metric tensor in either 3D or 4D. You don't really care about 4D, but whatever. And you'll usually see A given as the metric tensor in 2D. You will usually see Greek indices, so like G, lambda, mu. The Greek indices will usually be, or almost always actually, in 4D space or 2D space. So we don't really have to concern ourselves with 4D space being primarily mechanical engineers. And so the main takeaway is that if I was to write the metric tensor for a thin elastic plate or a thin shell, I would probably write something that looks like A alpha beta. And if I was to write the metric tensor for a blob of jello, I would probably write G ij, where the Latin symbols are usually denoting something happening in 3D. I'll try to put some more kind of notes to the side as we go. But okay, so here I'm writing down the line element in some undetermined, unwritten down coordinate system. Think of this as me standing here in this room, measuring the length of this object. Let's see there, this object, yeah, there we go. Based on, me standing here and saying, okay, well, it's this distance from the floor and this distance from the wall and that distance from that wall. And therefore the other end of this thing is, I can calculate the distances from it, the wall and the other wall and the floor, and I can write down what the length of this object is. If I know what's the metric that I'm living in a Euclidean space, and so I'm going to just write that as Kroneker's delta, and then calculate what the length of this element is. Get something like square root of dx squared plus dy squared is going to equal the length of this infinitesimal object, and then maybe I integrate along the entire curve to find the actual length. But you might be looking at my object from a completely different viewpoint, and maybe you find it absurd that I'm measuring it in Cartesian coordinates, and for you it makes much more sense to be measuring it in a different coordinate system. And so you might write down that the length of your object is going to be determined by, let's say, G bar KL. I'll make actually, I'm going to do this a little differently. You might say that the length of this object would be given by your metric, which has a bar over the top of it, and your corresponding kind of infinitesimals, which are also written with a bar over it. Now, physically, as an engineer or a physicist, you know that the length of this object does not depend on which choice of coordinate system we use. And so therefore, if these odd things are the same, if this and this are equal, well, then I can kind of take my object here and say, well, okay, if I'm measuring the same object, then I have to believe that there has to be some relation or some way to kind of connect Gij to G bar Ij, the metric tensor that I'm using and the metric tensor that you're using, so that we can both be sure that we're measuring the same distance, and so that we can switch between our respective coordinate systems to measure whatever we want to measure. And so we need to think about how to connect these two metric tensors together. And I point out that there must be some connection between these differentials. And this is actually, what I'm going to write down is actually something you've probably seen before, but in a different way. And you've probably seen that from just ordinary calculus, you might be able to take one of these differentials. Let's say it's dz, which we'll call dx3. So that's our like dz. And you know that from ordinary calculus, if I want to calculate dz, what I can do is I can calculate the partial derivative of that infinitesimal with respect to the three coordinates. So I'm going to take kind of, this is the one without a bar is my coordinate system, the one with a bar is your coordinate system. And so what we need to do to be able to convert between the two is to calculate from the product rule. We would expect something like this. We would add to that something like this. And if we're in 3D, we'll have how this differential changes with respect to the new 3D coordinate. We could go further if we want. We could say this would all hold true for and we also know by now that, well, if we're going to do this for dx1, dx2, dx3, we're going to get three equations, one for dx1, one for dx2, one for dx3. That's going to be related. Each differential is going to be related, a way to relate my coordinates differential to your coordinates differential. And we see something here. We see that really we're summing over 1, 2, 3, 1, 2, 3. And so we could write this more compactly as the sum from, let's say, I guess mu. No, let's do, what did I write down in my notes? Nu 1 to d of all these partial derivatives and their infinitesimals. And I think I'm missing a bar on all of these. So let me do that really quickly. No, we're not. We're good. We're good. This is the thing I'm looking at. Aha. You're probably confused. Hopefully you're less confused now. Okay. So the differential in the barred coordinate is related to the differentials in the unbarred coordinate. So this might be, you could think of this as like dr, for example. This could be like dr. This could be d theta. This could be d phi if we're living in spherical. And We want to go from spherical to Cartesian. And therefore, we know how to take my dx3 and write it in the barred system and write it in terms of the sum of the differentials in the other system. We can make this even further compact because we know we're going to get 3 equations here. We know we're going to get one of these for dx bar 2 and dx bar 1. And we can sum all of these 3 equations up, which each contain a summation in a very compact notation. And it simply looks like this. The new coordinate system's differential, dx bar, is going to be equal to the sum of all these partial derivatives of these differentials times the differentials in the other coordinate system. And what I want to highlight, just to remind you, is that we see there's a j downstairs here and a j upstairs here. Why is this one downstairs when it looks like it's upstairs on this x here? Well, it's 1 over that. So that's the equivalent of it being this kind of operation is the equivalent of it being a covariant index. We said last class too that the way to think of an example of a covariant vector or tensor is something akin to the gradient, and that's exactly what you're seeing here. So these are going to contract over each other. We're going to be left with an I on the other side of the equation because we have an I here, and that's exactly what we see. And this allows us to switch. So if I give you my coordinate system that I'm using, you can calculate its differentials in the coordinate system you're using. And it shouldn't be that surprising if I was to say, well, let's flip the order around. Can you tell me your differentials, and let's see if I can calculate them with respect to mine. And if we flip this around, we get something that'll look like dx I is going to be equal to the derivatives of dxi dx bar j dx bar j. These are really important. I lost my dot. These are really important, and they will help us switch between coordinate systems. How? Let me just first conceptualize these things for you a little bit, because I'm sure right now that they just look like a mess of notation. You can think of this as akin to, let's see here. We can write this. This is good. This object here has an I that's contravariant and a j that's covariant. So we could collect this as a tensor on its own. We can call that tensor Sij. And this tensor actually looks kind of like what you're used to seeing in linear algebra when you use a rotation matrix. So if the coordinate transformation is linear, and we're mapping between two kind of linear changes in our coordinate systems, then this reduces, if linear, this reduces to something you've seen before, which is like cosine theta, let's say in 2D. Sine theta, cos theta.
Can you repeat why the J is covariant? Because it's an upper index, so I think I missed that.
It's an upper index that's downstairs. So what that means is it's like let's see what I want to do this. You could think of this as like this operator. And here, this thing is in the denominator here, so it's kind of like the inverse of dx. So this is going to have, this is like an operator that's kind of like, I'll just call it dj, which would be like the partial derivative with respect to x in the j direction. So it's because you can think of covariant and contravariant, you know, in the sense as inverses of each other. And if you have something that's contravariant in the denominator, you're taking the inverse of that, so you get something that's covariant. Same thing. If you think of, if you took a covariant derivative variable in the denominator, and you therefore you're saying 1 over that thing, it's going to flip it to the numerator. This kind of notation here is really important, and this concept of the gradient being you know, gradient being a covariant operator. It's kind of the main way that people describe what a covariant vector is they say, well, look at the gradient. It's kind of, it's something that is going to covary with your change of basis. And usually it's that kind of gradient operation that gives you that. So it's covariant just because it's 1 over something contravariant. And so you're just kind of flipping that index. And we remember that we defined, for instance, we had defined the metric tensor as this, and we said, well, the contravariant metric tensor is just equal to, so you're really just kind of flipping those indices. And that means what's happening is inside the matrix, inside the tensor, like if you looked at the components of the tensor, you're really just taking 1 over them. And if you're taking 1 over all the rows are your, let's see here. I'll do it up here actually, so it's more clear. These are your kind of the rows, and these are the columns of your matrix. Does that help?
Yeah, thanks.
Okay. With these two things that I boxed in hand, we can now connect our way of measuring my way of measuring things to your way of measuring things. Because all we need to do is, let's see. All we need to do is say, well, my line element, ds squared, is equal to gij times dxi dxj. But I know that dxi is equal to this thing here. So I can write this as let me do this a different way. I know that I can say, therefore, the metric tensor G, let's say call it KL, that's the one that was in the barred system, times dxk dxl will be equal to my metric tensor, Gij, times, let's see here, this thing is this thing. And so this becomes dxi dx bar k. Then I have to do it again. The only thing I have to, so because I have two of them, I'm going to use the exact same thing up here. I just have to change the letters so I don't have them repeat. And I know what those letters have to be, because in order to get K and L on the downstairs over there, I'm going to need to have this be something like dxj. J contracts with this j, I contracts with this I, divided by dx bar L. And now the only thing we left off is these little differentials over here, and we're just going to tack those on at the end. So we'll say, okay, that means that we have dx bar k, dx bar L. We see that these things appear on both sides of the equation. And so I can simply say that this, the metric tensor that you're using, is related to, or can be transformed into the metric tensor that I'm using with this operation. In other words, I just need to take my metric tensor, multiply it by the derivatives of the vector that, say, parameterizes your coordinate system. That's this partial derivative here. I shouldn't use pink there. And here. And that will transform it to the coordinate, the metric system, the metric tensor that I'm using. So I don't want to do this to, let's see if we can do this quickly. Let's see if I can do this quickly. So for instance, if I'm looking at an example in which I have spherical coordinates. So I'm drawing a segment of a sphere. See how quickly I can do this. And these would be my, x1, x2, x3. We'll call these the barred system. Doesn't really matter. We could just switch our thing around. We could parameterize a vector in the spherical coordinates. You've done this before, undoubtedly. Just a little area on my sphere. And I can look at kind of angles, theta. And if I project this thing down, I would get an angle of phi. If I call my little vector from the origin to the edge of the sphere r, we'll call it r bar as my vector. Then this would be parameterized by something like this, r sine theta cos phi. I'm hoping you've seen this before in like a multivariate setting. Sine theta sine phi and r cos theta. And so this is my what I'm really trying to do here is switch between Cartesian coordinates, which is my green XY stuff, and spherical coordinates, which is my my sphere living in this blue r theta phi coordinate system. And so what I need to do is I need to take, for instance, calculate. So this is telling me I need to take derivatives of my vector. Let's see, which one am I doing here? I'll do it the other. I'll write down both of these for clarity. This is the other way to switch is like this. Let me see here. So what I want is I want to be able to calculate, for instance, dr bar by dr, dr bar by d theta, and then dr bar by d phi. And this operation is telling me that I'm going to need to dot those things into each other, along with dotting them into their diagonal. So once I've calculated these, so let's do the first one. The first one's pretty simple. Although I didn't leave myself a ton of room here. Let's see. So I could look at this and say, oh, well, this is just going to be, you know, sine theta cos phi, sine theta sine phi, and cos theta, right? Not too bad. This one's, I guess, a little bit messier, but not too bad. R cos theta cos phi, r cos theta sine phi, and negative r sine theta. Does everyone see what I'm doing? I'm just calculating these little derivatives here. And this one is negative r cos theta sine phi, r cos phi. Wait, what did I do there? I think that's fine. And then this thing is 0. And now we need to dot these things into each other. And I'm going to save you the trouble and tell you that if you dot the off diagonal terms into each other, you're going to get a bunch of zeros. So if I dot this thing into, for instance, dr, I'm going to get a bunch of zeros. But so we only have to dot these things into themselves. And dr d phi dotted into dr d phi. This ends up with a quite messy thing that looks like a bunch of cos squareds, sine squareds of thetas and phis. And I promise you, you do this out, it reduces quite simply to this. 1 r squared. And I would encourage you to, if you're interested in this stuff, to do these calculations out and see if you can match this calculation. But you'll end up with just these 3 terms are the only non-zero things after you apply some trigonometric identities. And it says that the metric tensor in spherical coordinates is given by 1 r squared sine squared theta. And there we just transformed from Cartesian coordinates to spherical coordinates. And I know I rushed through that. I would encourage you to see if you can do that calculation on your own. See if you can write in the parameterization for a cylindrical surface and see if you can transform from Cartesian to cylindrical coordinates, which will look quite similar to what we did with polar coordinates, but then you'll of course have the long axis for z there. So what, I guess? So, we transformed coordinate systems. Why do we care about knowing the metric tensor and different coordinate systems? And before I answer that, let me see if there's any questions I can help resolve.
When you change the coordinate system before you drew out the axes, where you define g bar KL, yeah, is that is the whatchamacallit, the superscripts, are they interchangeable with the so could you do dxi over dx bar L? And if not, how do you know that one corresponds to the other? Does that make sense?
Yes. So you're saying, can you switch this with this?
Yeah.
Yeah. The answer is almost always yes, and that is due to the symmetry of the metric tensor. I am hesitant to say that the metric tensor is always symmetric, but I will say all of the practical calculations I've ever done have used a symmetric metric tensor. And so
Okay, so by that standard whole matrix or symmetric matrices definitions from linear algebra, if you can say your metric tensor is symmetric, then it's valid to switch things around.
yeah, and I'm not confident enough in my ability to say that it's always symmetric, but in my experience, it always has been symmetric. So in that case, yes, you're basically just switching the order of the indices by switching those around.
Gotcha. So it's not that K and L are free indices, it's that it's symmetric. Okay,
Right.
thanks.
So why do we care about this? And the thing I will say is probably, actually not probably, the most remarkable thing about the tools of differential geometry is that if you know how to measure things where you are, then you can determine if the surface you're living on is curved or not. I say this is the most remarkable feature of differential geometry. It has a name. This is what's referred to as Gauss's Theorem egregium, which literally translates to Gauss's remarkable theorem, which tells us that you can determine the curvature, and in particular, what is referred to as the intrinsic curvature of a surface, just by being able to measure where you are. There's a lot of flat Earth conspiracies all over the internet and YouTube, and all you need to be able to do is measure the distances between points on wherever you are living. You'll be able to determine whether or not that system is flat or curved. Now, how? Well, it combines two things. First, you need to be able to measure, and second, you need to be able to determine the geodesics of that surface. Now, fortunately for us, we already know how to determine geodesics. We use the calculus of variations as a way to determine the shortest distance between 2 points on a flat manifold. All of those calculations can be done in this kind of more generic, less assuming notation that we're describing here. So we know how to calculate geodesics. We know how to calculate the quote unquote great circles, the shortest distance between 2 points on any arbitrary manifold. Now, why does that help us? Well, it helps us because of some fundamental ideas from geometry, which tell us that we know that if my space we know a lot about the rules of identifying 3 points on a surface calculating the shortest distance between any two of those points gives us a triangle. And we know that all the angles of that triangle add up to, what is it now? Now I'm blanking on myself. Pi or 2 pi? Someone tell me.
Pi.
Thank you. All the angles in here add up to pi. So if I take my angle, I'll call this one alpha, beta, gamma. So we know that alpha plus beta plus gamma equals pi. So that means that all I need to be able to do is identify 3 points on my surface and what you'll find and you can see it as I've drawn this this curved line here, is that this line is curved, this line is curved, and this line is curved. These are the shortest distances on a spherical manifold. These are the quote unquote great circles. Oh, that's a terrible circle. Pretend there's a circle there. And this surface that I've drawn here, something that's more spherical, more Earth-like, I can also write down alpha, beta, gamma. And if I add up all of these angles, which I can calculate these angles by taking the vectors that describe these lines, like the basis that those lines are running along, and dotting them into each other to get my angles in between these vectors, you'll find that for a spherical surface, the sum of these angles will always be greater than pi. And similarly, gray. This is supposed to touch. Similarly, if I draw myself a saddle or a negatively curved surface, and what I would find here if I take 3 points on this surface, and I calculate the geodesics between these points on this surface, is that they curve kind of like this. And I don't have room to draw my alpha, betas, and gammas, but you can pretend that they're there. And what you would find is if I add up all of the angles between here, I'll always end up with those angles being less than pi. This is done simply by being able to measure distances and angles on the surface that you're living on. That's why it's called intrinsic. If you're on this surface and you do not have any concept that there is a bigger world around you, so you are, this is always the analogy given here, so you are an ant living on this object here with no concept for the fact that you could leave the object. To you, if you were to take this object and measure triangles on this object, calculate, put down 3 points, and you're a really smart geometer ant, you could measure the distances between those points and the angles between those points. And what you would find is that this surface is not intrinsically curved. It certainly looks curved, but it only looks curved to us who are not on this surface, who are looking kind of at this thing from what's referred to as the embedding space. This kind of, pretend this is a 2D object. This object is embedded in a 3D space. And if I look at this object in my kind of zooming out from this embedding space, it certainly looks curved. But if I'm on here and I'm starting to measure distances and saying, okay, do I have, if I calculate a triangle, is that triangle going to add up to, have angles add up to pi or greater than pi? You'll find out that they add up to exactly pi. This space is intrinsically flat. This concept is captured, and it's the hallmark of Gauss's remarkable theorem, the Gauss's Theorem egregium, which is a way of saying there is an intrinsic curvature to each surface that we can calculate just by measuring lines and angles. And this intrinsic curvature is now referred to as Gaussian curvature. And it's usually denoted with a big capital K. And in the simplest sense, you can think of Gaussian curvature at a single point on each of these surfaces. So at a point, so we'll call it, I'm going to make a red dot to be clear here. So the Gaussian curvature at this point would be equal to, if I could denote that this is for perhaps the principal axis on this sheet of paper, and I could say how curved is that principal axis. We'll call it curvature kappa. Call it kappa 1. That's a little k. That's not a big K. That's super annoying. Sorry. Let me try to make it more kappa-like. Kappa 1. And the other principal direction will be here. I won't draw through my triangle. We'll call that kappa 2. This is equal to 1 over the radius of curvature in that principal direction. 1 over the radius of curvature in this principal direction. And the Gaussian curvature, the intrinsic curvature to the surface, can be defined at a point as the product between kappa 1 and kappa 2. So here, that Gaussian curvature is exactly 0. And you can see it. Go back to my cylindrical case. Look, here's my cylinder. If I take the curvature in this direction, which is clearly finite, it's clearly curved, and I multiply it by the curvature in this direction, which is clearly flat. This has no curvature in this direction, is curved in this direction. So the Gaussian curvature, the product of those two principal curvatures for this object, is 0. We can do the same here. We can say, well, allow me to measure kind of along the great circle here, kappa 1, and along the other principal components directions there, kappa 2. And for a sphere, we know that both of these principal curvatures, depending on how you want to define them, could be either positive or negative. It doesn't matter. Because when I take the product of those two positive things or two negative things, I'm going to end up with kappa 1 times kappa 2, something that's always greater than 0. And you can see where this is going. In this case here, I'm going to have something that is, I didn't draw my red point there. Do it here. If I come here and I draw my principal lines of curvature, I'm going to have one that looks like this in this direction. We'll call it kappa 1. And one that looks like it lives in this direction. Kappa 2. And now clearly one is going one way. The other is going the other way. So regardless of which one you choose to define as positive, the other one's going to be negative. Because this is like, let me just make that more clear. This is like a circle like this. This is a circle like this. And at that point, the normals to that point are going to have to switch. One's going to have to be up or down. And so we know that the Gaussian curvature of this hyperbolic surface is always going to be less than 0. Now, the reason this is important is that what Gauss's Theorema egregium actually says what Gauss's theorem of egregium actually says is that the Gaussian curvature, K, is invariant under local isometry. Isometry, what does that mean? Iso, isobaric, isothermal. Iso means the same. Isometry, isometric, means the metric is the same. So the Gaussian curvature will not change if the metric does not change. Let me say this another way. An isometry is a deformation that does not stretch a surface. It does not change the metric. What this means practically is that you can't switch between surfaces that have different Gaussian curvatures without stretching. And you know this. You know this incredibly well. If you've ever tried to, it's the holidays coming up for some, and if you've ever tried to put wrapping paper around a soccer ball, you'll know that it's impossible to do that without crumpling that paper. What are those crumples? Well, those crumples, the actual lines of that crumpled sheet, let me crumple a piece of paper over here. So my crumpled sheet here, if you were to take this thing and unpack it and look at those little kind of crumpled ridges along here, everywhere that you see kind of that sharp fold line represents a part of this material that was stretched. So the only way you're able to wrap your soccer ball with wrapping paper, the wrapping paper is clearly flat, it's a flat sheet of paper, we're wrapping it around a sphere. The only way you can do it is by changing the metric. there are basically two ways you can change the metric. One is you can locally stretch it. You can kind of plastically deform it, or you can fold it. And two is you can cut the material. So we're not allowing us to try to change, that also changes the metric, because if you have two material points that are a certain distance apart in your sheet of paper, and then you cut it and put those material points further apart, you've clearly changed the distance between those points. So you can't change the Gaussian curvature of a surface without stretching it. This has really profound effects and really helpful insights into mechanics, because, for instance, if you look at thin objects, you can write down the bending energy and write down the stretching energy. Think of those as the costs to bend the object and the cost to stretch the object. And what you'll find out is that that cost to stretch the object becomes more and more and more expensive the thinner the object becomes. Therefore, if you want to try to take a thin object and see what shape it's going to take when you deform it, you know that it's not going to change its Gaussian curvature, because that would be super expensive. It would much rather bend into a cylinder than it would be to be stretched into some complicated shape. Stretching is really costly for thin structures. Bending is really cheap. If we know that stretching is costly, and we know that the only way to change the Gaussian curvature of an object is by stretching it, then we know that if I have an object that's initially flat, I can't change it to being spherical without stretching it. Same thing, if I have an object that's initially spherical, I can't change it into something that is a saddle without stretching it, and same for a saddle to flat. This can be really helpful for kind of reducing the complexities of your calculations, because you know, well, these deformations would be impermissible, because that would require it to do something that would be extremely costly. And if we think about principle of least action, principle of minimal potential energy, we're going to do the path of least resistance. And we're going to avoid, thin objects are going to avoid stretching at all costs. Therefore, thin objects are going to try to maintain whatever initial Gaussian curvature they had to start with. Questions?
So if you change the Gaussian curvature, you're effectively bending or doing something out of plane to the object.
No, actually, if you change the Gaussian curvature, you are stretching the object.
So it's always some sort of stretching action.
Always some sort of stretching action. If you change Gaussian curvature, you are stretching. You might also be bending, but you are absolutely stretching. It's the only way to change Gaussian curvature. We use this as a really simple way to calculate. Actually, I should go back even before me. So, for instance, in the early 1900s, Stoney was working on a problem in which, and this is a problem that is still encountered a lot in any time that you're doing vapor deposition of some hot metal vapor onto a silicon wafer. So, you know, think of any kind of photolithography techniques that you might encounter. Whenever you're vapor depositing something onto a silicon wafer, your silicon wafer is flat and it's thin. And what happens is that you're putting down a bunch of material that's hot, and we know that as things get hot, they get expanded. So we put down a bunch of hot material that's all expanded on this flat, thin, circular silicon wafer. And then that material is going to cool. And as that material is going to cool, it's going to contract in all directions equally. And what Stoney showed, and this is something that was observed experimentally for a long time, which is that those silicon wafers will actually bow into a sphere if you're not careful. If you deposit too much metal, then as that metal tries to contract and shrink, it'll actually cause that flat sheet to bow into a spherical surface. Now that flat sheet could stretch for just a little bit. And if you kept going and you put more and more hot metal on there, and you had that thing shrink further and further, what you would find is that spherical kind of really shallow spherical dome, the cost of it continuing to stretch would be so enormous that it would buckle. And what it would buckle into is this exact sheet here. This is exactly what this experiment was. We took 2 sheets of rubber. The green sheet was stretched in all directions equally. We glued it to a pink sheet that was not stretched at all, and we let it relax. And what happens is you're trying to take something and turn it from a flat sheet into a sphere. We know that Gauss says that's not possible. That's going to be too costly, and so it's not going to be able to do that without stretching. We know that thin sheets don't like to stretch. They'll stretch a little bit, but then it'll become far too costly for them to keep stretching. And so what they'll do is they'll buckle, just like Euler buckling. You can try to compress a rod, you're trying to shorten its length. Shortening its length becomes too expensive, and so it buckles. And it chooses to kind of bend instead of continuing to stretch. And so this deformation here is the result of what happens if you try to take a flat sheet and force it to grow into a sphere. And what it'll do is it'll say, no, I'm going to find another way to deform. I'm going to deform in a way that keeps my Gaussian curvature the same, and therefore I don't have to stretch at all. And so that's exactly what it does. We tried to grow this into a sphere, and instead it grew into a cylinder because it was too costly for it to stretch. There's some more that we have to untangle here, which is how do we deal with the fact that this thing looks curved? And I'm telling you it's not. Well, I'm telling you it's not intrinsically curved. That if you're living on the surface of that cylindrical shell there, that to you, it would be the same as if you're living on a flat sheet of paper. Distances and angles would behave exactly as they would if you were living on a flat sheet of paper. You could measure the angles of your triangles and confirm that. But how do we reconcile the fact that, well, I mean, it certainly looks curved. So what I'm going to do is I'm going to first say, let's go back to our spherical coordinates over here. And let's say, let's say that we are living on a sphere. So let us live on the surface of the sphere. So if we live on the surface of the sphere, so our metric tells us, so if I write out kind of ds squared equals gij, oops, ran out of space. So our metric tensor in spherical coordinates tells us that the line element is going to look like this. And we know that we can call dx, we can parameterize our coordinates as r, theta, and phi. And we know what our metric tensor is. And so therefore we can kind of do all this out. I encourage you to confirm this for yourself, that that the line element in spherical coordinates is equal to dr squared plus r squared d theta plus r squared sine squared theta d phi squared. And that's squared. I left that out. Okay. So, oops. So here is the way to measure length in, with a sphere. If we tell us that we're going to live on a sphere, so for instance, we could say, I'm living on the surface of the Earth. I don't really care about measuring distances to the Earth's core. I really just need to figure out what's happening kind of on my surface. Is the Earth round or is it flat? If I need to measure the Gaussian curvature of the Earth, I don't need to care about what's happening in the thickness direction. And so we can say, well, let's allow us to, we don't care about changes in R. And so we can say, well, we'll just get rid of any concern for changes in R. And we'll say, well, let's let the radius be a unit circle, the unit sphere. So we're living on a sphere in which we say it has a radius of 1. It doesn't matter. We could keep it as a variable, but it just kind of, for our sake of simplicity, we can just say, let's pretend it's 1 for now, and we don't lose any generality there. And so therefore, the metric reduces. Our distance on the surface of the sphere just becomes d phi squared plus sine squared, d theta squared plus sine squared theta d phi squared. So just to be clear, this is on surface. And therefore, we would write our 2D metric, the metric tensor on the surface of the sphere. Remember, in 2D, we usually use A to represent the metric, and we usually use Greek letters to denote that we only have 2 coordinates to worry about. So we would say that A alpha beta would be equal to 1, 0, 0 sine squared theta. That's our metric in 2D. Now we only live on the sphere. A brief aside, why we care about this, just to remind you, if I take an object, if I take this thing, here's an object that I could put coordinates on the surface of, and I could write down the metric. It would be in polar coordinates, perhaps, since I'm, or cylindrical coordinates, I suppose, since I'm living on something that is, it's curved like a cylinder. But if I stretch this thing, then I'm going to have material component coordinates that could get what they say convected along with that deformation. You can't see, but pretend I'm stretching it. And the difference between the metric tensor in the deformed state and the original state is exactly the strain tensor. So if you've taken elasticity theory and you say, okay, well, I have my, if I take A alpha beta, which is my original, and I say I'm going to call A bar alpha beta my deformed, the difference between those distances from my deformed state to my actual state multiplied by a factor of 1/2 is exactly equal to the strain tensor. Usually it's written, you're probably used to seeing epsilon there, but I write gamma because this is technically what is referred to as the green Saint-Venant strain tensor. So this is just a brief benefit of being able to measure distances on surfaces, is that it directly relates to mechanical quantities like strain, stretching strains, curvature strains, and so on and so forth. Okay. So we're living on this surface, and we've talked a little bit about curvature in really general terms. This Gaussian curvature defined as these principal curvatures. But we need to be a little bit more thoughtful and careful about how we define this so we can return to our dreaded or perhaps beloved tensor analysis. And we could say, okay, well, how do I actually, if I'm standing on my surface, how do I kind of more mathematically measure curvature? If I don't want to go and calculate the distance between here and Rome and Buenos Aires, how do I actually calculate the distance on a surface at a given point? And what you can do is you can say, well, here I have some curvilinear coordinate system, which we'll call x1. So I have some curvilinear coordinates that run along the surface of A. So they run along the surface of my sphere that I'm living on. This is my x1 coordinate. Perhaps it's, in this case, theta. And I know that the basis vector in the x1 direction, we've been calling it A1. And at every point, I should be able to construct a normal to that point, right? I should be able to say, well, there's something here that's not living on the surface. We'll call that A3. Why not A2? Well, A2 is the other coordinate on the surface that I'm living on. So you can imagine this as a slice of a sphere, in which I'm kind of saying, well, there's also probably some other coordinate maybe that runs like this way. And this would be like the x2 direction, and then I could have like a basis vector there as well. But for right now, let's just focus our efforts on this kind of slice of my surface and say, well, what does curvature mean? Curvature means that if I was to march along x1, I should be able to say something about how that vector rotates. And the rotation of that normal vector should tell me how curved it is. If I move between 2 points on x1 and my normal stays the same, well, then I'm not curved at all. If I rotate in this way, I'm going to be, let's say negatively curved. And if my normal rotates this way, I'm going to be, say, positively curved. So we need to be able to calculate this normal. And fortunately for us, we know how to calculate normals. And what we need to do to calculate the normal is to say, well, the normal should be proportional to the cross product between A1 and A2, which is the cross product between these two basis vectors, dr x1, dr x2. And to be fair, we want this normal vector to be a unit normal. So we need to actually say that our unit normal would be this cross product over its norm. So A1 cross A2 over the norm of A1 cross A2. And so if this is our unit normal, and we want to be able to determine curvature by measuring kind of the change of that unit normal, then we're going to want to measure the curvature as the change of the unit normal in the x1 direction and as the change of the unit normal in the x2 direction. Okay, so what does change of that unit normal mean? It means that we should be considering the partial derivative of alpha, the partial derivative of A3 with respect to x to the alpha. So this is shorthand notation that I defined earlier up here, where I say that delta sub j is equal to d whatever, the operator d over dx to the j on whatever I'm operating on. So here I have this, you could think of this as dA3 by dx to the alpha. So that's just step one. I want to determine how my vector, how my vector is curving as I go along the x1 direction. And so what I'm going to do is I'm going to say, well, let's calculate how much this vector is changing as I move along the x1 direction, and then project that, the length of that vector, down onto the x1 direction. So that'll give me a sense of, as I'm moving in this direction, this vector is changing, and I'll just project that new vector, that kind of tilted vector, I'll project that onto the x1 direction. And I could also project it onto the x2 direction. So if I kind of am moving this way, I could project it onto x1 and x2. Projection is the dot product. And the dot product in this tensor notation looks like this. Which we're going to take d alpha A3, which is the change in my unit normal, and I'm going to project that onto A1 and A2. And you know from your tensor notation that if this quantity here has a covariant alpha and a contravariant beta, which means this has to be equal to something. We've used A, so let's call it B. And that's going to have an A downstairs and a B upstairs. And for sign conventions reasons that I don't remember where it comes from, people often refer to this with a negative sign. So what is this B thing? Well, it's clearly a matrix or a tensor. It's clearly second order. It's not a vector. It's got two indices, two legs. It's going to be a tensor of second order, a 2 by 2 tensor. And what is it? Well, this is kind of how you can calculate it, but you're more generally going to see it defined like this. And it would be defined as, in terms of the second fundamental form, in which we write the second fundamental form is 1/2 B alpha beta dx alpha dx beta. Now that probably doesn't help you, but we've just said that B alpha beta is a 2 by 2 tensor. And what are the components of this tensor? Well, I'm going to write it out, and then I'll tell you what it is in a second. It's usually written like this, which when I first saw this, I was like, well, that doesn't help me at all. LMMN. But let me show you what you should think about this. You should think about these as, this is going to be essentially a Hessian, a matrix of second order derivatives. So why second order derivatives? Well, you can think about why you would have a matrix of second order derivatives by the fact that what you're really doing is you're saying, okay, I've got a point in space P, and it's living on some curved space that's maybe locally spherical. And I should be able to draw at any point on my surface a tangent plane to that point P. Tangent plane. And what I'm looking for is to determine, kind of like, as I move along my surface here, how far down am I going relative to that tangent plane? Oh, that should have done that in a different color. How far down have I traveled away from my tangent plane? And once again, so what that means is this has some direction, some coordinates in the z direction, and some, we don't know, it's some location z, which is a function of, I don't know, x1 and x2. And the simplest way to kind of, in general, write down what z is relative to that tangent plane is to do a Taylor series expansion about that point, which we'll call the origin. So we'll do a Taylor series expansion about x1 is 0 and x2 is 0. And this Taylor series expansion, usually you'll see it written down where it skips a bunch of steps. You're going to see it like this. You're going to say, well, I can write f of x1 and x2 as being approximately equal to 1/2 x1 squared times the second derivative of f of 0 and 0 plus x1 x2. This is just a Taylor series expansion, but we're neglecting the first order terms. I'll tell you why in a moment. And then obviously there's higher order terms here. So this is a Taylor series expansion. It's a quadratic form because all the things we have here are to the second power. And these terms here, this, and this are, for the sake of making our life easier, just collected and saying, well, we'll call that L, we'll call that M, we'll call that N. And instead of looking at these things at some finite point in space, we'll look at them in terms of their differentials. And so therefore, you'll see the second fundamental form written as L dx1 squared plus 2m dx1 dx2 plus n dx2 squared. What happens to those other terms that we're used to when we do a series expansion? We're used to seeing stuff like f at 0, 0, and we're used to seeing first derivative, so it'd be like df x1 and df x2. Well, what happened to those? Well, if my tangent plane has a slope, which is what these things would mean, right? These things are saying slopes. If my tangent plane has a slope at the origin, it's not a tangent plane. So they have to be 0. And we've already set it at the origin, so the value of my function at the origin should be 0 as well. So the first terms that you're used to seeing in your Taylor series expansion are all 0. This is 0 kind of by definition. There's really nothing lost by translating or moving this whole thing around. And then these refer to the slopes in the 1 and 2 direction. But I've said I'm looking at a tangent plane. The tangent plane can't have a slope at that point. x1, 0, x2, 0. Okay. Why do I care about this matrix over here of L, M, and N? Those Hessians, those second derivatives. Second derivatives of deflection are related to your curvatures in those directions. Your principal curvatures are therefore the eigenvalues of this matrix. I have a 2x2 matrix. I should have 2 eigenvalues. And here's how you'll typically see them written. You won't see them with L and M. You're going to see them like this. You're going to see that I could take the trace of my matrix. Now, this usually throws people off because usually people are thinking, ha, I know the trace of a matrix. Trace of a matrix is just the sum of the diagonals. Once again, that's only true if you live in flat space. No one tells you that in linear algebra because you're always dealing with stuff in flat space. But in reality, the trace of your matrix is the contraction of the metric tensor with the curvature tensor. Well, I should say that a different way. The trace of a matrix in curved space is the contraction of the metric tensor with whatever tensor you would like to calculate the trace of. The trace of the curvature tensor is the contraction of the metric tensor with the curvature tensor. So this thing is going to give you, let's say we can contract the alphas to leave it with something that's like this, 1/2. What did I say? I said, no, let's contract the betas. So we'll contract the betas, so we're left with b to the alpha alpha. And what's the second eigenvalue of a 2x2 matrix? If the first one is the trace, the second one is the determinant. Once again, you've been led astray. The determinant, the second eigenvalue of your 2x2 matrix is the determinant of the matrix divided by the determinant of the metric tensor. Det B is the over det A, which doesn't really have a lovely way of writing it. It looks like this: B11, B22 minus B12, B12. Now, if you're following, then you might say, well, wait a minute. Earlier, he said that the Gaussian curvature is the product of the 2 principal curvatures. If I have 2 principal curvatures, that means I have diagonalized my matrix and I'm only looking at the eigenvalues. And so therefore, this thing down here, where I have kind of the product of these 2 principal curvatures, that means this quantity here must be the Gaussian curvature. The Gaussian curvature is one of the 2 invariants of the curvature tensor. So what's the other thing? Well, the other thing is the other invariant of your curvature tensor. And the other invariant of your curvature tensor is what's referred to as the mean curvature. And here is where we resolve that conundrum of why is this thing look curved, but I'm telling you it's not. This is your intrinsic Gaussian curvature. This is your extrinsic, meaning you can only see it from the embedding space, mean curvature. And you can interpret this as the sum of the curvature in the one direction plus the curvature in the second direction. So in this case here, the principal curvature is 0 in this direction. But the principal curvature in this direction is some curvature, let's say 1/r. So the Gaussian curvature is 0 times 1/r, that's 0. But the mean curvature is the average 1/2 of 0 plus 1/r. And so this structure is curved, has a curved mean curvature, has a non-zero mean curvature. It's not a flat sheet of paper. It is curved if you're able to view it from above the surface or outside the surface from the embedding space, but it's locally flat. So it has a finite mean curvature and a zero Gaussian curvature. The last thing I want to do with the 10 minutes remaining, since I'm just throwing a bunch of stuff at you, I highly encourage maybe re-watching these two videos together, and maybe that'll help, or reaching out to me and seeing if I can help via email or chatting on Zoom. The last thing I want to do is talk a little bit about calculus on these surfaces. And I want to I'm doing this because there is one, if this hasn't scared you off, there is one last thing that surely might, and I kind of want to just dispel any mystic notions around it in case you ever encounter it in your research. So to do calculus on these curved manifolds, I just want you to first kind of remember what some of the operations you're used to actually do. And I don't know, I've never really seen this taught this way, but this is how I think of it. This is how I conceptualize these things. So we're used to things like, I want to be able to calculate gradients. I want to be able to calculate a divergence. I want to calculate a Laplacian. These types of operators emerge as we start to derive the governing equations of whatever system we're looking at. And I think it can be really helpful to think about these operations as kind of changing the order of your tensor. So a gradient increases your tensor order by 1. If I take the gradient of a scalar, like I take the gradient of the temperature in this room, I take the gradient of a scalar, and the output of that is a vector. So this goes from a gradient takes something as a scalar as an input and spits out a vector. But more generally, you can also take the gradient of a tensor, or say, let's say this a different way. We can also take the gradient of a vector, and that's going to give me a tensor. And we know from the first lecture that a vector is really just a first order tensor, and a scalar is a 0th order tensor. So really, we're just kind of increasing the tensor order. A divergence is doing the opposite. Your divergence is decreasing tensor order by 1. So a divergence is going to take a vector and spit out a scalar. Or it'll take a tensor and spit out a vector. So what does your Laplacian do? The Laplacian is the divergence of a gradient of some object, which means that if you think about that in order, the gradient of the object is going to increase the order by 1, and then the divergence is going to decrease the order by 1. So the Laplacian maintains the same tensor order. If you ask a Laplacian to operate on a vector, it spits out a vector. If you ask it to operate on a tensor, it spits out a tensor. You can see this in the notation for a Laplacian. If you look at the way it's written in a tensor analysis form, is you would write the Laplacian, for instance, the Laplacian of a vector as grad mu of my vector v lambda. Now look, we know by the rules of all this stuff that these are going to cancel out. I'm going to be left with a vector. If I do Laplacian of a scalar, then I contract over mu, and I'm going to be left with a scalar. So this is going to give me like a new vector. We'll call it b lambda. We'll call this thing v. The reason I bring all of this up is to kind of help ground you in what these operations are doing. Because the most confounding thing you'll encounter in differential geometry and tensor analysis is the covariant derivative. And if you've never seen a covariant derivative, well, it looks like something like this. It looks like grad. So this will be covariant derivative. So we'll call it it's grad with a subscript, is identifying this as a covariant derivative of some vector. So we'll just call it like a vector v hat. The problem here, let me illustrate the problem mathematically really quickly, and then I'll explain it to you conceptually. The problem is what you're trying to do is well, let me take the partial derivative of my vector v. Well, to do that, I'm really saying, well, I want this operator to act on my vector v mu, v lambda, which is living in with some basis vector e lambda. And the problem is, in curvilinear coordinates, both your vector and e can depend on x. And so you know that if you're trying to take a derivative of two things that both depend on x, then what you have to do is you have to do the product rule. And you have to say, okay, well, this is like d mu v lambda times e lambda plus v lambda d mu e lambda. And this is the thing that's a problem. You have to take the partial derivatives of your basis vectors, which means that in general, you have to take the partial derivatives of your metric tensor. And that leads to what are referred to as Christoffel symbols. And these generally terrify everyone from first-year graduate students to full professors. But let me try to demystify it with the last minute or two I have left. The covariant derivative, the simplest way to conceptualize the covariant derivative is to think about trying to calculate money changing over time in which there might be inflation. So if you're saying like, how much is my salary changing over the next 20 years? What you need to do is say, well, my salary is going to increase hopefully by some amount, but I need to add to that the change in the basis vectors, which is the change in how we measure money. So I'm going to not only consider how is the money changing, I need to consider, well, how is the value of that money changing? How is the money changing relative to the way that we measure the value of money inherently? So a covariant derivative is an ordinary derivative plus something that calculates the change in the reference frame. I need to know how much my vector is changing. And then I need to know how much my basis vector is changing. Why? Well, you're usually introduced to this with the concept of parallel transport. And you say, well, I have a x1 coordinate here. I am going to plop I don't want to do that. I'll take my tangent vector. Here. And if I move that tangent vector along the curve, well, it's no longer tangent. So I have to take my tangent vector, which might be my velocity, and say, well, as I parallel transport my vector, if my basis is changing, I have to account for that to actually measure how my vector is changing as it moves along that curve. I can't just look at the way that the derivative, the rate of change of that vector. I need to consider the rate of change of that vector and the rate of change of how I'm measuring that vector, so the basis that it's under. And so your covariant derivative adopts this really horrendous form in which you say, I'm going to take the covariant derivative like this, which is going to be equal to my ordinary partial derivatives, things that I'm used to doing, plus this horrendous symbol, capital gamma, which has 3 indices. These are your Christoffel symbols. We won't go into what they are or how to use them, but you should be able to, if you followed this class, be able to maybe introduce yourself to them in a less terrifying way. These represent derivatives of the metric. But again, this is just ordinary derivative plus how are the things that I'm measuring changes against changing along the way. My salary is increasing over time, but the value of money is also changing over time. So I need to compare, if I want to know how my earning has changed over some amount of time, I need to consider both how has my salary changed, how has the value of money changed, how has the way that we measure the worth, the value of money changed. The two of those things together will actually give me the appropriate measure of how my money has changed over time. I'm over. I'm happy to hang out for a few minutes if there are questions. I try to cram a ton in here. Again, I just wanted to give you a really crash course in differential geometry. And hopefully this serves as like a jumping off point if this is ever useful to you in the future. So if there are questions, shout them out.
So that B matrix going back like several sections, written in blue, that's the that's sort of whereas the previous ones we were looking at were transformations between bases. That B matrix you could sort of think as setting up transformations between the derivatives of bases.
I guess so. I would say these are the components of the curvature tensor, and really what they're doing is they're second derivatives of your normal with respect to the coordinates that you're living on, and they're going to tell you how curved is your surface in this direction, how curved is it in this direction, and what's the kind of how curved is it in those off diagonal directions. So if A alpha beta tells you how to measure distances on your surface, B alpha beta tells you how to measure curvatures on your surface.
Okay. And then that Christoffel symbol thing, I've run into stuff called, I guess, is that basically just a derivative of an entire space definition is what you're saying?
it is, you know how here we have something that says, look, you need to also think about this just from the product rule says if your basis vectors are a function of x, which if you have a curvilinear coordinate system, they are, then you have to consider your typical partial derivative, and then something that considers the partial derivatives of your basis vectors. Now I looked at this in one direction, but more generally, this means I have to consider partial derivatives of my metric tensor. And so therefore, let me write out the Christoffel symbols. So Christoffel symbols, capital gamma, mu, nu, rho looks like this. So it's got your metric tensor, rho sigma as the partial derivative with respect to mu of your metric tensor, plus the partial derivative with respect to nu with your metric tensor, minus the partial derivative with respect to sigma of your metric tensor. And it'll take you, so this is don't worry about where this comes from or what this means or how to use it yet. The only thing I want you to see is that the covariant derivative consists of your regular derivative plus things that account for changes in your metric. These are just derivatives of your metric tensor, which you know how to calculate. Like, you know your metric. It's, you know, I scroll up here, here's my metric tensor. I can do derivatives of in my three main directions.
Right.
Calculate my Cartesian, sorry, my Christoffel symbols from these derivatives. Most people like myself will just kind of go and look up what the Christoffel symbols are in a particular coordinate system. But if you're feeling really ambitious that day, you can go through and calculate it all from scratch. But the takeaway I want you to have is when you're living in curved space, you need to consider derivatives of your vector or tensor, as well as how is the metric changing, or how is the basis is changing in the directions that you're moving as your vector is kind of transported along those. As your vector change, how does the way we measure your vector change?
Gotcha. Thanks.
All right. Thank you, everyone.